Okay. I'm sorry, technical problem. Yeah, it is solved. Okay. I hope that you can see my screen, and I'm going to talk about optimal control, energy and time optimal control today. And my example would be about robotics, but I'm talking about in general about any dynamic system, especially multi-degree of freedom. This work has been done by some of my colleagues, like Professor Alam, Rehan, Hormuz, Pavel, all of them, my dearest colleagues in RMIT, and I'm representative of this work. Okay, let me make this small, put it here, and like this. Okay, very well. I put abstract of the topic here on the second slide. I'm going to share the slide with you so you can read that later. It's not important at the moment. Well, I'm going to talk about that today. But before starting the technical problem to explain, let me share with you my regret that I'm not able to attend the conference in person. I cannot forgive myself for this missing, and these are some photos of Dhaka. I have a lot of good friends. Many of them were born from Dhaka, so I had a great chance to see Dhaka for a while. Unfortunately, there were some other business that prevented me to attend this conference in person. So you please enjoy Dhaka for me. Okay, I'm going to start by introducing myself, my background. For me, it is interesting to show off and review what I have done. And then I switch to the technical issue or problem that I'm going to discuss. Upright, you see me in my office here at RMIT, and I always look at the bottom right figure to understand that we are nothing in this world, actually. So after introducing myself, I'm going to talk about optimal control in general, time optimal control in particular, and what is the main issue and problem in optimal control. And then I introduce a method. I called it floating time method that I invented by myself 25 years ago. And since then, I was working with that. And then maybe we can discuss about future direction of this problem. But as a reminder, please remember to turn on your mobile phone when you leave the session after this discussion. Okay. At the moment, as you can see, these are my appointments. I am a professor working at RMIT University School of Engineering. And meanwhile, I'm also adjunct professor of Waterloo University in Canada, one of the best universities in Canada, actually. I was lucky to be a postdoc working Waterloo for 2 years around. I learned many things from Waterloo University. Also, I'm adjunct professor of Xiamen University of Technology, one of the best universities in technology in eastern part of China. Also, there is a very interesting university called Ocean University in Xiamen, Fuzhou, that I am honored to be adjunct professor over there. Okay, me personally, I like to be called an expert in nonlinear vibration, in nonlinear mathematics or applied mathematics. But still, I feel that there are many things to learn. For education, I was graduated in 97 in nonlinear vibration and applied mathematics. And then before that, master's in robotics and bachelor in internal combustion engine, actually. some industrial experience. I've done several projects for Nissan, Kia, Audi, and Peugeot. All of them are automotive industry. So my background, industrial background, are mostly related to automotive. Very well. I was lucky during the past 30 years, 20-something years that I was in academia. Was lucky to have collaboration with many universities all around the world, some European, many American, Canadian, Asian universities, Middle Eastern universities, and it is around 10 years that I am in this region, Australia. Out of these, you can see several Chinese, Indian, and other universities named here. The figure on the left bottom is me teaching at North Dakota State University in 2004, around 18 years ago. That was taken by one of my students while I was teaching. I was teaching control, I guess, and it was in the lab of thermomachinery. Well, good memory from North Dakota State University. As I said, mostly I like to work in nonlinear vibration, nonlinear dynamics, applied mathematics, and engineering-related problems. I explain some of those problems. Here you see the list of some problems that I'm still working on that, and you can see one of them says floating time method, the one that I'm going to explain today. I wish you can see my cursor here. But before going to floating time method, I'm going to introduce to you the very interesting problem that at the moment I'm working, me and my colleagues, the team that we are working on drift. And it is very interesting. Well, that photo that you see is me while I was postdoc at University of Waterloo in year 2000. That was my office. Okay, this is drift. Very interesting action, very interesting behavior. If it is controlled well, it is artistic driving. Well, maybe few percent of drift is that beautiful. 90-something% goes to accident. So in general, for non-expert driver, drift is dangerous. We must be able to predict drift and prevent drift in general. Well, I put some interesting figures here or animation video for you to enjoy drift, to get attracted to this problem. Here in bottom, probably you can hear the sound. This video was taken in Raleigh, Kenya, I guess 2 years ago or something. Very interesting one. And here is another one, bottom right. This is us, means one of my students who was working on drift had this experience to go to a class to learn drift here in Melbourne. Some of funny drift is here. Look at this. The guy is drifting with tractor. There is no sound. It's like dancing with tractor. It was fantastic. Look at this one. This one is even more fun. But now that you have seen that drift is an interesting problem, let me explain what we are doing on that. to be able to define drift mathematically, we are working on that. If eventually we come up with an equation to express that this equation measures drift, or let's assume that when it is positive, we get drift, when it is negative, it's normal driving, or vice versa, it doesn't matter. So when this equation, which is related to some kinematics information coming from a vehicle that we can measure by sensors and put every variable in that equation and then measure the resultant, and when it is getting close to zero, we are getting close to drift, and there is a warning system in vehicle that is connected to a computer like ABC, for example. Not ABC, I forgot the name, ABS, like ABS that takes the control from driver and act something to prevent wheels to get locked during the braking. So we need such a system to implement, to take the control and do some action to prevent to go to drift, because drift is beginning of losing control and go out of the road. So if we do this, we save a lot of lives. But at the moment, this is the situation of technology or science. We do not have a mathematical definition for drift. For many years, many people are working on that. There are some suggestions. None of them are general, and we are aware of all of them. We tried many of them. At the moment, we are working on this simulation. Anyway, this is out of the question for today. I just gave you some information about what at the moment we are working on. Okay, I like to publish books. That was my dream since I was in elementary school. So as you can see here, I was lucky to get the opportunity to write books since 2006 when I moved to America. And then every year almost I was able to publish a couple of books. The top are those books that I published by myself as single author. The bottom are books that I was collaborating with other authors, like Professor Liming Dai from University of Calgary, and other people that you can see their name on the book. Anyway, my advanced dynamics is coming out probably before end of December or before end of January in 2023. Anyway, out of these books that you can see, these two are very, very famous. Well, famous means according to the market. To me, all of those books are fantastic. But these two, according to market, are very famous. Many universities, maybe more than 100 universities, adopting these two books for teaching robotic and vehicle dynamics. And because of that, they have been also translated to several languages. Here you can see Chinese version of these two books. I was lucky to do some services. These are something that we as academic usually do, to be associate editor of journal. This is a volunteer duty, and we are pleased to do that. Usually we are honored to do that. Based on my working as an associate editor in several journals that you can see here, some of them, in 2012, I decided to publish a new journal that I thought it's a missing part of journals, actually. I called this journal Nonlinear Engineering, and for 6 years, I've been the chief editor of this journal, and then I put it to other people to continue. So Nonlinear Engineering is something that started 2012, and it is 10 years, which is publishing. Okay, anyway, let's go to the problem of optimal control, time optimal control, and energy optimal control. As you can see, I'm talking about optimal control of energy or time. So it is not necessarily related 100% under the umbrella of this conference, because here we are talking about thermodynamics, energy conversion, and this sort of thing. But I'm talking about energy optimal control. Means we have a dynamic system. From some state, it's moving to another state, and we wish to do this time optimally, energy optimally, jerk optimally, or whatever is criteria for optimal control. We can prove, at least for a single rigid body or single particle, that time optimal control and energy optimal control are equivalent. Very interesting. Just these two, not other things like jerk optimal control. Well, jerk is derivative of acceleration, and jerk is a measure of shape. That's reminding that I'm using jerk, so you understand what is the meaning of jerk. Anyway, jerk optimal control is also important. And if you search my name with jerk optimal, you can see some of papers that I published related to that. Anyway, consider a system. It means one particle. Here, upper left, 4 equations are the equation of motion of a single particle with mass m equal to u of t. U of t is not University of Toronto. U of t means force or input, which is function of time, minus k sine of v. V is velocity, k is coefficient of friction. So here we have a mass, external force with friction and with air resistance, which is c dot v. So we have a mass, a force, friction, and air resistance are applied. We wish this mass move from some point to the other point time optimally or energy optimally. Now, there are some constraints. Whenever we are talking about control, optimal control problem, constraint comes. Let me give you an example. Let's assume that a mass from 0 to 1 meter is supposed to move in minimum time, and we are applying a force. If force can go to infinity, the time goes to 0. It's not practical. It's not physical. In reality, that force has a maximum. And if the condition is rest to rest, means here we stop, at the end also we stop. I'm going to talk about this problem. So end condition and constraint on input or other kinematic characteristic. Like, for example, we have a limited input. Limited means there is a saturation. There is an upper limit or lower limit for the input. And also, we wish to go from here to here. Maximum speed is something. Okay, so it means another constraint with maximum speed or maximum jerk or maximum acceleration is also applied. So constraint can have a variety. The simplest one is limit on the input. Here on the bottom of left bottom, you see constraint that we apply. Usually u, look at u, which is input. U has a limit between minus u hat, and on the right hand side is u hat. So here we assume that maximum, minimum force, the absolute value are equal, and force can vary between these two. On the right column, you see conditions. So there are some initial conditions, which we are starting from x0, can be 0, with velocity equal to 0, so it is rest condition, and initial force is u0. And finally, wherever is the final, which is indicated by xf, xf is given to us, so the path of motion is given. The time for the final is tf, whatever is TF, that our goal is to minimize TF. At TF, we know where we are. At TF or XF, we know velocity is going to be 0, so it is rest condition again. And force at the end is known. So this problem is a very simple explanation of rest-to-rest condition constraint input. Now look at the minimum time problem. Minimum time problem, mathematically, optimal control is always going to an objective function. Usually we show objective function by capital J. And we define that with an integral. Integral of something during the whole motion must be added together and J must be minimized. Now, if that integral is over dt, integral of dt would be t, so it means total time is supposed to be minimized. If it is energy, then energy, if you assume that energy is here in this system, is about kinetic energy, for example, then 1/2 mv squared dt is integration over energy. M can be assumed 1, so we can always transform the equation, whatever the system, to have m equal to 1. It is always possible. So these two J, one is J time, the other one J energy, they must be minimized. And based on that minimization, we determine force. The input is supposed to be calculated at any time. Okay, and we are able to show that these two are equal. Because of this, that I'm skipping that part to show that these are equal, I stick to minimum time problem, because all of other optimal problem of dynamic system starts with time optimal control. When we learn that, we are able to apply whatever I'm going to explain about the method of solution to other type of optimal problem. Okay. As an example of dynamic system, let's assume that we are talking about a 2R robot. 2R robot means a robot with 2 revolute joint. Revolute joint, we abbreviation is R. So we call it 2, means 2, number 2. Capital R means 2 revolute joint. On the bottom, I said a 2R robot moving along a given line. Let's assume that the end point, we call it end effector, the hand of the robot. Here I don't have a hand. I have 2 links attached to each other. One motor is on the ground. The other motor is on air. So the second motor, respect to the first arm, changes the direction of the second arm. And first motor on the ground is moving everything together. Okay. Usually, the end effector or end point starts from some point, we call it P1. It's supposed to go to P2. The path of motion is designed by us, not by the robot. So we select the path. If it is straight, it is like left figure. If there is an obstacle, there is a forbidden area that the hand is not supposed to go through, then we have to design a path to go over or below, doesn't matter, to go around the obstacle, the forbidden zone. How we design that path is another topic, which is called path planning. For us today, let's assume that path planning is done. A path is given to us. For simplicity, I'm going to ignore any forbidden area, and I'm going to move from a given point P1 to another given point P2 on a straight line to explain the problem. But it is in general applied to any other type of problem which has different path of motion, with obstacle or without obstacle. Okay. One more time, some mathematics here. The optimal control is generally, it's a part of calculus of variation. And you know that calculus of variation is a science or a calculus or a new branch of mathematics that Euler, the Swiss scientist or Switzerland scientist, made it in 1700. And he started, I explained what was the motivation to invent this part of mathematics. But this part of mathematics, besides the problem that Euler originally started or motivated to solve and invented this mathematics, after that, this mathematics was based for optimal control. Anything, whatever is optimal control is related to calculus of variation. And it is, logically, it is simple. Means we have a functional like J, the first line. The first line is J, which is integral of a function, whatever is the function, like energy, as you can see in the previous slide, or 1 as time, or any other function that we wish to optimize. It is not necessarily related to physical system. It can be something that you made it by yourself and still it is valid. There are some boundary conditions for this problem. Means x, which is variable, is given at t0, which is initial time, and tf, which is final time, and we are supposed to minimize whatever is j, the integral. Euler said that let's assume that we have the solution, and that solution that we are looking for, we don't have it, but let's assume we have the solution and indicate that solution with x star. So here, x star is the solution that we are looking for, and that solution is the solution that minimizes the functional j. Now, Euler said, let's assume that we add some perturbation. Perturbation means we have something big, I'm talking about variable, and we add a very small, tiny, with the same characteristic of the main variable. If it is time, we add special time, very small time, or whatever is x. So second line, you see that we introduce a new variable, x, which is not optimal. It is optimal plus epsilon y of t. Epsilon is very, very small, tiny, and y of t is another function which we call it perturb or perturbation, multiplied by that epsilon. That epsilon guarantees that x of t is very close to x star. Deviation or differential between these two are very tiny. When we substitute that x into the functional and do the minimization and expand based on epsilon, exponent of epsilon, we come up with delta j, third line. Delta j means the difference between optimal j and non-optimal j because of introducing epsilon y of t. That delta of j would be a function, a polynomial based on epsilon. The first coefficient of epsilon is called v1, which we call it first variation. Okay, first variation, and then epsilon squared, capital V2. V2 is the second variation. We ignore the rest of them, just these two, focus on these two. Well, to make delta j equal to 0, V1 must be 0, V2 must be 0. If we go for V3, V4, all of them must be 0. But because epsilon itself is very small, after epsilon squared, nothing is important. So they are 0 already. Epsilon to the power of 1 has a coefficient V1. Look at the first variation. First variation, as you can see in that integral, that's Lagrange integral. That's the way that we derive the equation of motion in dynamics using Lagrange method. Okay, second variation is a little bit more complicated, but let me remind you, I'm sure that you are aware of all of these. These are something that we teach in undergraduate or master's program in mathematics usually. So you are aware of that. I'm just reminding for some students who probably are there and listening to me, and probably these material are new and they need a review. Let's go to calculus, and in calculus we have y equal to f of x. We take derivative, we call it y prime. Derivative y prime equal to 0 gives us an equation that equation equal to 0 gives us some x. Those x are extreme value. Extreme value means minimum or maximum value of function y. So imagine that y as a function of x has a curve, okay? There are some point maximum, minimum. To find the point, what point? X value of those maximum, not the value of maximum. The x value associated to maximum and minimum, y prime equal to 0 is the equation that gives us that. Gives us the x value for maximum and minimum. If we wish to find the actual value, we put that x into the function and measure the y value. At the moment, this is not my concern. My concern is this: how do we know which x is maximum, which x is minimum? We go to second derivative. If second derivative, you remember y double prime. If second derivative is positive, we teach students and we say that it can hold water. And second derivative is related to minimum of the function. If second derivative is negative, we say that function cannot hold water. It is like a cup upside down. And here is associated to maximum. That's the trick that you remember. What does that mean? Back to calculus of variation. First variation gives us the function, actually. But second variation talks about stability of that function. Okay, I talked about that problem too much. The motivation for calculus of variation for the first time optimal problem or time optimal control problem, if we call it, appeared by Bernoulli. What was the name? Johann Bernoulli in 1696. At the end of the 17th century, 1696. Bernoulli, you know that Bernoulli was a family, several brothers and father and grandson and so on, all of them geniuses and mathematicians. So Bernoulli introduced this problem. Actually, that problem initially was introduced by Galileo 50 or 60 years before that. And Galileo didn't have any mathematical proof for that. But by experiment, he found a wrong solution that I'm going to talk about. Let me get back to this. Brachistochrone is the name of this problem. Bernoulli said that assume that we have a gravity, G, okay? And in a vertical plane, there's a point called P1. There is another point called P2. So this is initial, this is final. And between these two, we are having a wire. Shape of wire is not going to change. So let's assume that this wire is made by metal, okay? And it is not like a chain. It is just solid. So path of motion is fixed. Now we have a bit frictionless, slides on that curve and goes from P1 to P2. What shape of this curve has minimum time of travel? That was the problem that Bernoulli started. Later on, he himself and his brother Jacob, I guess, solved this problem. And there are a lot of mathematicians around at the same time solved this problem with different or very close methods, like Newton himself, Bernoulli, two brothers, Leibniz, another German genius guy, and finally Euler and Lagrange. But the method that Euler solved was different. As a suggestion, if you haven't read this book, which is Differential Equation with Historical Note, if I am remembering the name of the book correctly, written by Simons. Fantastic book, especially talking about Brachistochrone problem. He in that book explains how it can be solved by Schnell principle. Schnell principle is the principle that we use in light, and we understand that the light is going to break when it goes to another media with another density. And we know that tangent of the angle of entering and tangent of angle of exiting are equal, and so on. Based on that, the ratio relates to density, and that ratio is related to speed of light in different media. So using this, breaking the ray of light when it goes to another media with different density, he simulated, or he reported, not himself, he reported that somebody did this, that moving from P1 to P2 is similar to moving to denser and denser, or media is gradually going to be denser, and path of motion would be the path that light is going to take because of Snell principle. Snell principle says that light goes the path, picks the path with minimum time. That's the relation between behavior of the light and this problem. Anyway, that was just recommending a book to read. What was that? Differential equations with historical note, Simons. If I remember correctly, it was McGrahy, 1970s something. I don't remember correctly, but you can find it. Anyway, they solved, all of those scientists that I mentioned, they solved that the path is cycloid. And cycloid is a path that when a circle is rolling on another curve, let's assume that that curve is at the moment is a straight line. So it is the circle is rolling on the ground. Any point of the periphery of the circle makes a path. That path is called cycloid. Here on the bottom, you see the path or the cycloid in red. So that path gives us the solution of brachistochrone. Any point to any point. As far as P1 and P2 are connected by a brachistochrone, it is the minimum time. And here on the right, you see the solution. As you can see, J, which is integral of dt, and dt is going to be substituted by ds over v. S is the path of motion, v is velocity, and then because it is under gravity with no friction, velocity is always a square root of 2gy, and ds, as you remember from calculus, it is a square root of 1 plus y prime squared dx. So we convert everything instead of dt to be ds, which is j here, and then we apply Lagrange method, which I showed you as first variation equal to 0. The result would be that equation, y as a function of r was the radius of that circle, and finally we can introduce the equation by parametric method, parametric here beta. So x and y, both of them are function of beta. Beta is the angle of rotation of the circle. So these two, when you plot them, you find brachistochrone. Anyway, the solution is in any book related to calculus of variation. My point is that that was the first time optimal control problem introduced by Bernoulli, and it was generating or initiating the approach that Euler took to introduce calculus of variation. And calculus of variation was the mathematical base for all optimal control after that. We can talk about brachistochrone path for hours. It's very magical, very interesting, and it is fun to play with. On the left figure, as you can see, between A and B, there are different paths. One of them is straight line, which probably we guess it must be the first solution for minimum path, but it is not. You see the green one, which is circle, part of circle. That was the guess of Galileo. Galileo guessed that circle, or an arc of a circle, gives us the minimum path. Now we know that cycloid is the minimum path. Here, as you can see, there are 2, 4, 5 5 bits are starting at point A together, no friction on different path, and as you can see, the black one reaches point B sooner than others. And as you can see, green goes next. So Galileo's guess was very intelligent, very smart guess, actually. We can talk about that pendulum, that pendulum, the period of pendulum depends on initial deviation, means initial amplitude. More amplitude, less, more period. Period is time of one cycle. But if the core is leaning on cyclic wall, then we are able to see that no matter what is the initial deviation of the pendulum, all of them have the same period or same frequency. And here on the bottom, you see that different point of cyclade, we have several beats, we let them go, all of them get to the end at the same time. Very interesting to show all of them. Usually we show them in the classroom for people. Let's get back to our problem. Our problem is moving a dynamic system from one point to the other point. As an example, simple one, to introduce the method, let me focus on a mass. Here, top view, the mass is, for example, a car. Look at the car. The car is going from x0 to xf, so the distance and the path on x-axis is given. It's one-dimensional motion. Rest to rest, so it is supposed to be at rest beginning and at rest at the end. There is no friction. The only constraint that we have on the left-hand side bottom, you see that force has a maximum and minimum limits. So the force variation between capital F and negative capital F. The equation may have friction. Look at the second equation on the left, which says F is equal to mx double dot minus mu mg. Mu is coefficient of friction. First, assume that there is no friction, means mu equal to 0. If we have such a system, you understand that the solution would be applying the maximum force from the beginning of the path up to the middle of the total path. At middle of the path, we have to switch to the minimum, means negative maximum, to break the system to be able to stop at the end. So accelerating to the middle, braking to the end. This is mathematical solution to make sure that the car is going to stop, the mass is going to stop. And this is what we see as the solution. Force is maximum and then switches to negative maximum, or let's say minimum, okay? And for this problem, I assume that maximum force is 10 Newton and assume that total mass is equal to 1 kilo. So this is the solution for no friction. Now let's assume that there are some friction. Friction helps to break the system. So instead of switching from maximum to minimum force, we must force the mass a little bit more than center. Because when we switch to braking, the friction is helping us to stop the system. So depend on friction value, the point of switching, you understand switching is when force is switched from one saturation to the other saturation value. This is one solution with friction. So the red one, we push the pedal more than center. To find switching point is a challenge. If it is one-dimensional, we are able to find switching point analytically, although it is not that simple, but analytically we are able to find that. So that's the problem that I'm going to explain. As I said, so far, analytically, we are able to solve one-dimensional problem. But how about multi-dimensional, multi-degree of freedom? Here is shuttle arm. This shuttle arm simulates the hand of human. You know that the hand of human has 7 degrees of freedom. 7 degrees of freedom. And you know that to catch something in three-dimensional space, we need 6 degrees of freedom. And 6 degrees of freedom means 3 translation and 3 rotation. So we are able to control any object at any point, at any orientation. That means totally 3 numerical values coordinate to go to a specific x, y, z, and then 3 rotational angle to go to the orientation we wish. So in general, we need 6 degrees of freedom, but hand has 7 degrees of freedom. 3 on the shoulder, because shoulder can turn in 3 directions: 1 direction, 2 direction, 3 direction. So shoulder has 3 rotational degrees of freedom. It's like a ball and socket joint. And then at elbow, we have 1 degree of freedom, as you can see here in this figure, elbow joint. 1 degree of freedom, which is rotation. Then we go to wrist. Wrist also has 3 rotational degrees of freedom: 1 rotation, 2 rotation, and 3 rotation. So in general, hand, like this arm, has 7 degrees of freedom. I can talk about what is the advantage of having 1 extra degree of freedom and why we have that extra degree of freedom, which is out of the question. Anyway, my point is having a dynamic system which is multi-degree of freedom. How can we solve optimal control of such a system? Here is spherical wrist attached to a robot, which is called articulated robot. In totally, we have a 6 degree of freedom robot. Majority means 90+% of the robot that we are using in industry have 3 degree of freedom or less than 6 degree of freedom. We don't go with more than 6 degree of freedom in industrial application. Special lab or experimental or research, we can go to under-actuated or over-actuated robots. That is out of our topic at the moment. Let's take a look here on motion of this hand, just to give you some rest. And I continue the topic. This is called spherical robot, and I give you the source where to learn about kinematics, mathematics of this robot. And here is a Stanford arm or a spherical robot, as you can see. And here is the simulation of some motion of that robot, which is not important to us. Everything comes to this genius Russian guy. Let me explain again. We have a dynamic system, multi-degree of freedom. Every degree of freedom, you imagine at least a 2R robot, okay? 2R robot is multi-degree, at least 2 degrees of freedom. The problem is that there are 2 motors, both of them has a limit with saturation, means maximum force that they can apply is limited. Now, the tip point of the robot is supposed to go from one point to the other point, for example, on a straight line. We do not know when and which one of these robots are supposed to be saturated and the other one within the limit. Remember, if both of them are saturated, the tip point is definitely not going to follow the path that I wish. When the path is supposed to be traced, these two has a spatial ratio at any time. That ratio is going to change. So let me say that these two must have different values in general. We cannot solve the optimal control analytically to understand which one has the switching point to go from maximum and minimum, and at any time, which one is supposed to be saturated. But Pontryagin again proved very interesting fact that is our guidance. When I explain what Pontryagin suggested or proved, you understand that, yeah, it makes sense. Well, Pontryagin proved that optimal control of dynamic system or mathematical system with limited inputs has minimum time motion when at any instant of time, at least one of the actuators is saturated and all other actuators, actuator means motor, are within their limits. So none of them is going to break their limit. But we do not know at any time which one is saturated. So switching points are unknown. But at least if there is a numerical method that we can develop such a path that at any time at least one actuator is saturated and the rest of them are within their limit, that's the solution. There are not two solutions. There is only unique solution, one solution. And if you find that solution with any method, that's it. So my point is to introduce the method, one method that I invented to solve such a problem. But we have this theorem, Pontryagin principle, that guarantees what we found is the only solution of the problem. Okay, I skipped this part just to save time, which I explained here. What is time optimal control based on Hamiltonian and so on, which is not important. I go to the method that I made, and I called it floating time method. This is based on finite difference. As a reminder, when we want to solve differential equations numerically, you know that there are some methods in finite difference, many methods. Okay, the simplest one is forward difference, which you see on the left-hand side. Euler introduced that for the first time. I'm talking about 300 plus years ago. Euler introduced that, and still we call it Euler method. But he himself also and others developed backward difference as well. It means, let me explain in forward difference what is the point. The point is that we have a curve here in plotted by blue. Okay, blue is actual curve. What we want is the slope, true slope, which is the black line at what point here introduced by x sub j. So at x sub j, we wish to find the slope. Slope means that straight line that touches the curve at that point. Okay, and the slope means arc tangent of the angle of that line respect to x-axis. So slope at point x sub j is what we are looking for. We are able to have the value of curve means the blue, at another point, which is another forward point, which is xj plus 1. Let's assume that the value at xj plus 1 and a value of the function at x of j, which as you can see in numerator of this fraction here, f at xj plus 1 minus f at x of j divided by the difference between x of j plus 1 and x of j. Let's assume that on the x-axis we discretize with the finite difference. Differences are equal usually. We call it delta x, or as simplicity, to be simple, we call it h. Okay, so h is the increment on x-axis. If h is going to approach 0, point x of j is there because we are looking at it. The other point, which was forward, xj plus 1 and f at xj plus 1, when h is going to shrink, that point is approaching f of x of j. When these two are very close to each other, that f prime, this equation on the bottom, is equivalent, very close to the value of the slope that we are looking for. This is called forward difference. Similar to that, we are able to introduce backward difference. So instead of a point in forward, in advance, we take a point in the back, and then we approach that point to this point. We can apply both of them and measure two values of approximate slope and then make average of them. That's another trick. There is another method called central difference. So in central difference, which is the right one, we have 1 point in advance, 1 point in the back, and we do not care about point at the middle, which is the interesting point. These 2 points together are going to get close to each other. Okay, so that central difference method is what I'm going to use. Now let's assume that the curve is given to us, and on the horizontal axis it's time, vertical axis is y. The previous one, vertical axis was f of x, horizontal axis was x. So let's assume that x is time. F of x is a function called x. Here, I'm talking about position versus time, okay? Let's assume the path is given. It is not, but let's assume the path of x versus time is given to us. We are looking at ti, okay? And we are looking for slope at ti, means velocity at ti. Another step in forward is ti plus 1, and step in the back is ti minus 1. But the difference is not constant. My point is that I assume that these differences are not equal and are variable. So I assume that all t's are given to me, x's are given to me, but delta t are not. So by shrinking and expanding ti, changing the variable ti, time associated to that, let's say ti plus 1, is getting closer or going further, but x value are not moving. So I'm introducing or reintroducing the equation for central difference, which is velocity. On the right-hand side top, you see numerical value of velocity at point I, which is xi plus 1 minus xi minus 1. These are the value of position divided by total time difference. Total time difference is tau I plus tau I minus 1, which is indicated in the figure. Tau is time difference, which in Euler method we call it h, or delta x, or delta t, which was constant. Here they are not constant. So x values are given, tau value, which I call it floating time, are not. Similar to that, we are able to calculate an equation for x double dot, which is acceleration. One problem with central difference is that beginning at t0, on the bottom you see that, beginning at t0, we need a point in time which has never happened. We start at t equal to 0, but for central difference calculation, we need a point before the motion starts. The similar problem is at the end. When we stop at ts plus 1, we need another imaginary point in the future. After we stop, after we finish the motion, there is another point called ts plus 2. This is normal or well-known problem in central difference or any type of finite difference that those people who are familiar with, especially those people who are working in fluid mechanics or numerical method in fluid mechanics, they know that we can increase the number of imaginary points in the future or imaginary point in the back, and there are some algorithms to start evaluating those points. Then we begin the numerical analysis. Here, I'm going to explain what would be the value of ti minus 1 and x minus 1. Also, what would be the ts plus 2 and x at s plus 2. But regardless of this problem, you understand that I'm going to use equation x dot and x double dot for velocity and acceleration. It's a little bit complicated, but I give you the reference to go into it. It looks complicated, but double use of x dot gives us x double dot. So that's the trick to find. Let's get back to this problem that we showed what we expect as the right solution. Now look at on the bottom, look at the x dot equation. The problem was supposed to be rest to rest. If it is rest to rest, velocity at t0 must be 0. So velocity at t0 must be 0 means numerator of this equation must be 0. It means x1 and x minus 1 must be equal. Imaginary equal, because there is no x minus 1. Just the value must be equal to that. So we found a value for x minus 1. Also, because we are going to solve minimum time, whatever is tau 0, tau minus 1 must be equal to tau 0. If tau 0 is minimum, x1 and x minus 1 are equal, so tau minus 1 is also equal to tau 0. So these are information to start the algorithm. Similar dialog goes to the end point. Tau s and tau s plus 1 are equal, and x at ts is equal to x at ts plus 2. Although physically it's impossible, numerically we can substitute those values. These are given on the bottom that you can see. Now, let's assume that we are talking about one mass, no friction, for simplicity. The equation of motion is just F at I means the point discretization, equals to M, which is constant, x double dot at I. Starting at 0, this is the equation. F0 is equal to M x double dot 0, and x double dot 0 from central difference would be 4M divided by 2 tau 0 squared, parenthesis x1 minus x0. X values are known to us. The only thing that we do not have here is tau 0. Now imagine that tau 0 can be changed. I changed tau 0 until f0 would be equal to maximum f. Why? Because we know that at the beginning we must start with maximum saturated input. So tau 0 in denominator is in my hand. I change this until it adjusts to f0. So tau 0 calculated. Now I can go move to second point. In second point, tau 1 is unknown. Now I change tau 1 until f is going to be saturated and moving forward. Okay? So this is the principle. I assume that we start with saturated input and I adjust all time intervals to keep this at the maximum. Let's go to not the endpoint, but endpoint, means one step before endpoint. At the endpoint, I know that I'm supposed to be stopped. And I know that at that point, force would be braking force, so negative maximum. So the value at endpoint is known based on the principle that I need over there to be braking and stopping. 1 point here and 1 point here. Up to this point, I'm talking about the last 3 points. Up to this point, force was maximum. At this point, force is negative maximum. Here, at this point, there is no unknown tau, because this one found to make this maximum. This found, I'm talking about time difference, has been found to make this one negative f. So here, there is one f value out of my control. I just substitute one tau from right-hand side, the other tau from left-hand side in the equation and calculate the value of force. That force definitely breaks the rule. Why? Because I was forcing the object up to very close to the endpoint, and at endpoint I have negative f. This time is not enough to decelerate, to brake, to stop there. We need a huge force negatively. So what is going on? That breaks the rule. It is not the solution. Now, I know that here at the end, I must have negative f. So out of these 3 points, I take this f out From here, I move to here with negative f. Now I have another 3 points. That here, f positive, here, f negative. The value of this f must be calculated from the equation. If it breaks the rule, I keep going backward. If it is within the limit, this is the solution. So this is the strategy. So you can imagine that when I do this, on the backward calculation, I must go up to the middle of the path. And in the middle of the path, I get 1 point that the f value is within the limit. I can make this accurate by increasing the number of increments. Let's assume we start with 220 increments and see the principle, and then numerically we go to 2000 increment to have the value very accurate. I explained everything here, and let me skip that. And this is the example that I'm going to solve. The curve that I'm going to show you is based on 200 increments, but the mass is 1 kilo, maximum and minimum force is 10 Newton. What else? Rest to the rest condition. And this is the algorithm. Let's take a look on this animation that I explained the method. So this is the beginning value and end value. On vertical axis is the value of force input. Horizontal axis is the path, x. I'm moving one-dimensional, no friction. So I start here and find the time interval, floating time. And I know that at the end point, I must have minus f. Now you see the last 3 points. The middle one requires one value for f, which is huge, breaking the rule. It's not the solution. So I take this one, out and move backward until I find the right solution. Done. I don't know, maybe 20 section. A very limited section just to show the idea. Now, if you increase the number of these increments, the solution is showing one jump exactly in the middle. This is what we expected the solution. Now, if we have friction, the equations would be different, but the method stays there, and jump or switching point is going to be found somewhere on the right-hand side of the middle point. This is called bang-bang control. Funny name, but bang-bang means switching from one value to the other value, saturated value to the other saturated value at no time, like instantly. Okay, we solved, or I solved this problem with other friction. Look at this. I'm talking about the mass with friction. When there is no friction, mu equal to 0, I'm switching here, which is in the middle of the path. You don't see in the middle because when we have no friction, the solution ends here at 0.6. There is nothing on the right-hand side. Horizontal axis is time. When we introduce friction, you understand that the total time increases. Switching point is shifted after the right side. So you see mu equal to 0.2, 0.6, 0.4, up to 0.8, and total time are calculated here. The minimum time is for no friction, and here for t equal to 0.8, we go up to 0.977. Let's assume that it is second, but everything was dimensionless, so it is not that important. This is the method, and it is applied, at least for one-dimensional system, which, as I said, we are able to solve it analytically. Same problem, different view. It is f value on vertical axis, x value on horizontal axis. That's the best, because x was supposed to be between 0 to 1 meter, or 1 unit of displacement. When mu equal to 0, we exactly switch at 0.5, as you can see, at 0.5. by increasing the friction 0.2, 0.4, 0.6, 0.8, the switching point shifts to the end. Here is x as a function of time, which, as you can see, it is close or similar to, I don't know, arctangent or paired cubic function. Doesn't matter. This is what we get. All of what I said can be set as an algorithm, which here I put all of them in algorithm. I skip the explanation of this algorithm. I give you the reference. But there is something which is called convergence. How do we know that this method converges to the solution? Well, there is a theorem how we can find the convergence. I proved the convergence, and I put it in a couple of papers, and in my book that I'm going to show you, I skipped that. Believe me, it converges very well. Is it just time optimal control of robot or one mass? No, it is not. The main purpose was applying to multi-degree of freedom. But as a test, I applied the method to brachistochrone. Is it possible to find brachistochrone by this method? Let's remember that although there is an analytic solution, in numerical solution, we do not know at any y value what would be the best x value. So this is the approach. And when we solve this for g equal to 10 meter per square second, and SS is the number of increment, 100. An analytic solution is here. And as you can see, there are two paths, means two endpoints. First, start from y equal to 1, x0, goes to x equal to 1, y0. It's not in a scale, okay? That's one solution. And the other solution is starting from 0, 1, goes to 2, 0. So two different examples. And the solution are here. Analytic solution is here, TF1 for the first path. Here is another TF, which is found by analytic solution. Sorry, this is analytic solution. On top, you see the solution or the value of time based on floating time method. Second one, TF2 and TF2 here. One is for analytic solution. The other one is numerical solution based on S equal to 100. Change S number of increment to 1,000. TF2 and TF2 or TF1 and TF1 get closer and closer. But these are close enough. Engineering point is good enough. This is the brachistochrone. Now, for multi-degree of freedom, we do this. I'm going to add what I said in the algorithm. Let's assume that the first motor, first actuator, assume that it is 2R robot, okay? First actuator is maximum in the first increment, okay? So I found tau1 to have Q1 or M1, whatever is called the name of this motor. Let's say moment 1 is saturated. Now I have T1, and I'm able to put all tau in the second equation and calculate the value of torque in the second motor. If that value is not breaking the rule, breaking the limit, that's the solution. If it is breaking the limit, then I forget about that. I go here and make tau somehow that this motor is saturated and come back, calculate the value of this. Definitely 100%, this one is within the limit. That's the solution. Now I go to next step. Because it was saturated, I assume that for next step, this one is also saturated. So I found tau1 for this one, saturated. Now with that tau, come here and calculate the value of this. If it is not breaking the rule, that's the solution. If it is breaking the rule, then I forget about that. I adjust tau1 to make this one saturated and calculate the other one. If we have multi-degree of freedom, we start with the first one. maximum and calculate all of the others. Anyone that breaks the limit, I capture that, I take that and make that one maximum and calculate the rest of them. If none of them is breaking the limit, that's the solution. If any one of them is breaking the limit again, I take that one and make it maximum. So with this trick, every step, I'm able to calculate all torts and find out which one is maximum. Looks very simple, very applied. So this is the algorithm, and all of them are introduced in this book very well. One chapter dedicated to time optimal control. I explained everything in detail with a lot of mathematical proof and example and so on. You can read that by yourself. Let's show one applied problem. Let's go for 2R problem. 2R manipulator, robot, planar, very simple, but mathematically it has everything. If you prove one method of control on 2R robot, usually you are able to apply to any type of robot as well, or any type of dynamic system. It's highly nonlinear. It has everything we want, or we can add whatever we want. Here, I assume a 2R ideal robot. Ideal robot means arms has no mass. And we have one M1, as you can see, which is the mass of the motor in air, and one M2, which is payload, or whatever is the mass that robot is capturing and moving. And motor 1 is on the ground, which the mass of that motor is supported by the ground and not important. The dynamic of motor, let's ignore that. You know that the motor has a rotor, and rotor has inertia, and that inertia and friction can be added to the equations. Here I ignored all of them because our point is to prove the concept. The tip point is moving from 1.5 to -1, 1.5 on a straight horizontal line. Okay, and we have two motors. The algorithm to make this equation of motion, which I call it P and Q. What is P and Q? Back here. On the left side, you see P is the motor, the value of torque of the ground motor. Q is the value of torque on air motor, the motor which is moving on M1. Okay? Okay, these two, P and Q, are equal to some differential equation in terms of theta and phi. Instead of measuring or name it as theta 1, theta 2, I went with theta and phi. And as you can see, theta is the value of the first arm with the ground, and phi is the value of the angle of the second arm with respect to the first arm. So the equation here, one is absolute variable, the other one is relative variable, but it's out of our question, what is the difference between them? Anyway, these two equations can be, equation of motion of the 2R robot can be set like this, and capital A, B, C, which are coefficient, are given below. As you can see, those coefficients are related to variables, so A, B, C are not constant. For example, A is a function of phi, as you can see, and other things are parameter, M1, M2, L1, L2, which is the length of the, they are constant. The only thing is phi variable. I do see the last one, capital M, capital N, are function of theta and phi, both of them. Anyway, so at any step, theta 1 and theta 2 must be calculated based on inverse kinematic, because the path of motion are given to me, and that value of theta 1 and theta 2 are going to be here, and new set of coefficient goes to the equation of motion, and then over there I have tau, means floating time, tau 1, tau 2, and so on. I'm going to adjust them to set P or Q to be saturated. That's the way. Another step, we calculate again from inverse kinematic the new value of phi and theta, put them there, new coefficient of the equation, and this loop is going to be calculated to the end of the motion. One point, tau is just one-dimensional related to time, so same tau time interval goes to all of the equation. P equation or Q equation, both of them have the same variable of floating time. Again, as I said, velocity and acceleration are here, substituted, and some limits. Let's solve the problem for M1, M2 equal to 1 kilo, L1, L2 equal to 1 meter, maximum or limit of P and Q, both of them 100 Newton meter. And this is the solution. Solution for that straight path. As you can see, this solution with that numerical value says that the motor on the ground must be saturated from the beginning up to some point that it switches to the minimum to stop the robot at the end. The motor on air has some value within the limit at any time. That's the solution. Now we find the switching point. Let's find or solve the problem for another path to see if it is possible that the other motor is also get saturated. Well, saturation depends on the value that we define. Here, I assume that these two motors are equal, not necessarily equal. The other one can have the maximum of 50 Newton meter. In that case, you see that at some point here, the red line goes beyond 50. If I had that constraint, then switching point was multiple. But still, let's take a look on the solution, simulation of that solution. Same problem, going straight, minimum time. That's the minimum time. This is another problem, example, that it's stretched to 1.9 on x-axis, and it is coming back to 0.5. Y value is always 0. Same physical parameter. This is the solution. And interestingly, you see that at the beginning, the motor on the ground is saturated up to this point, which at this point, the other motor, the second motor on air, gets saturated negatively. Up to this point, that again, the motor on the ground gets saturated negatively, and the red one is within the limit. One more switching point is here that the motor on air gets saturated negatively. Eventually, the path finishes rest to rest condition. So these are the conclusion that I explained, that numerical solution of time optimal or energy optimal or jerk optimal control, any optimal control of multi-degree of freedom is not possible analytically. We must develop numerical methods. There are some numerical methods. That was one of them that I made it, and I called it floating time method. It works very good. And when we design that, when we solve this problem for a robot, then that robot, what is the solution? The solution is that we derive the curve or the value of motors or actuators at any time, okay? Then we dictate those values by computer to the actuator. And the robot is moving from the beginning to the end according to minimum time. Well, this was very simple explanation. We must add some other realistic parameter to the equations of motion, and there must be a feedback because at the moment this control is blind. We apply those torques and we assume, we expect that end effector is moving from on the path that we designed from the beginning to the end point. What happens if, because of some disturbance, like wind, for example, the end effector is deviate from the path? There must be a feedback to measure and adjust the system. Here, I didn't talk about the feedback problem. So there are a lot of other sub-problems that we can add to this problem, but this is the main solution of time optimal control of multi-degree of freedom system. Thank you very much for listening. I wish I was there to answer your questions. It's interesting topic, or any other part like drift, for example, vehicle that I mentioned something, or anything else that you can imagine. You're welcome to email those questions, or I wish that we have another chance to meet and see each other, and then if I can answer your question. I wish you enjoy the rest of the day in this conference, and then later on when you have time, have a tour in city and enjoy Dhaka as well. Thank you very much and goodbye.